Hello, my name is Roy Simpson. I'm an instructor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a bunch of lectures I have on intermediate algebra, and specifically on polynomials in intermediate algebra. And this lecture is based on graphing quadratic equations. So that means graphing equations that are like y equals something with an x squared and something with an x possibly, but at least something with an x squared. We're going to break this into two parts, a part A and a part B. Part A will be all the simple cases. And that would, I call them the simple cases because they're really kind of the easiest ones to graph. And then part B will be the other 98% of the cases that we run into in mathematics. So really the simple cases are going to be quadratic equations that are very quick to graph, and but they're not very common. And part B is really the one that's important. So what do I mean by simple cases, the simple styles of quadratics that we can graph? Well, first of all, we know that a quadratic is of the form, so I'm just going to write it up above so that we don't confuse this as a simple case, but a quadratic equation is of the form y equals ax squared plus bx plus c, where a is not 0. That would be a quadratic equation. The simple cases are cases where we are asked to graph something like y equals ax squared, or possibly y equals ax squared plus c. Essentially, the simple cases are anything without the middle x term. So what do I mean by simple cases? Really, where b is equal to 0. And what we're going to do is investigate these kind of slowly. If you are taking a course in intermediate algebra and you already know about transformations, reflections, and shifts, and compressions, and stretches, and all that fun stuff, then this video is going to be kind of useless to you. However, if you need a review of that, you can watch a little bit of this. I'm not really going to talk about them in my general format. I'll wait until a little bit later to talk more in detail about shifts, translations, and reflections, and stretches, and compressions. But in this video, we're going to take our time going through just what does a number or a coefficient on x squared mean, and what does that c do to the picture as well. And then in the next video is the one I really want everyone to watch. It's the best way to graph a parabola, or a quadratic equation, really. The first thing we're going to do is graph this basic function y equals x squared. I call that a basic function because in the long run we're actually going to call this the base function or the base graph for all parabolas. And we'll explain that a little bit more in detail a little bit later on. But for now, go ahead and build a table of values. And when you're building a table of values, for anything other than a line, which since the power on x is not 1, I know this is likely not to graph out as a line. Whenever you're plugging in points, you want to plug in at least 5 points. And I'm going to try to keep it symmetric, about 0. In other words, I'll plug in like -2, -1, a 0, a 1, and a 2. Now, you could plug in more points than this if you want. But it's important that for now we keep it symmetric about 0. If you don't, you won't get the entire graph, or you won't get the pattern for the entire graph, maybe I should say. It's easy to see that when I plug in -2 for x, y will be positive 4. When I plug a -1 in for x, y will be positive 1. When I plug in 0 for x, I get 0 for y, and then 1 for x leads to 1 for y, and 2 for x leads to 4 for y. So I'm going to quickly draw a Cartesian coordinate system, and I'm going to label my x-axis according to the scale that I chose here. So I'll call this 1, this 2, and therefore back here this will be -1, and this is x equals to -2. And I will also label my y-axis accordingly. I'll call this 1, 2, 3, and 4. I even have more room. Actually, I could have spaced them out even better than that, but for now I think that's pretty good. I'll choose an obnoxious color for the plotting of the points. So when x is negative 2, according to our table, y should be a positive 4. And when x is a negative 1, y should be positive 1. And if you only plot 2 points, you'll think that this is a line. That's why plotting more than 2 points is extremely important. When x is 0, y is 0, and it still looks like this might fit on a line, but as you go to your next point, x equals 1, y equals 1, you realize this is not a line. When x is 2, y is 4. Now you want to connect these points, but before I do, I'm going to go ahead and label these points. This was negative 2 comma 4, and so on and so forth. I'll just quickly do these. Notice I rarely ever label the origin. It's just something that I choose to not label because it's right on the origin. I'm not a big, I don't really care about that. And now when you connect these points, a lot of people might initially think you just connect each of these points with a line. It turns out that you don't. When you're graphing any type of equation, things generally want swooping curves. So I'm going to connect these with curves like this. That looks like a line, but it's actually supposed to be sort of curved. Okay, so far so good. I want to make a mention here. If I had plugged in x equals a negative 3 and x equals positive 3, our outputs would have been 9 and 9 in either case. And if you think about that, this is x equals a negative 3. 9 is, well, let's see, this is 5, 6, 7, 8's probably here, 9's probably way up here. So it would have been way the heck up here. Okay, so just note that it starts climbing pretty quickly. I'm not really going to draw that on the other side. I'm just going to do it like this. That shape right there is called a parabola. And it's a very important shape actually in the real world. That's essentially why, for those of you who have some type of satellite service on your TV, it's why you can actually watch TV. It's because your satellite dish has this parabolic shape to it. It may not be this curved, it might be a lot wider than this, but there's a special property that parabolas have that really make them very useful. So we'll talk about that later on in my lecture series. But for right now, just know that they're one of the most important shapes in use today. Now what we're going to do is show you what other versions of y equal x squared looks like. And specifically, let's start with like y equals something like 3x squared. If you've watched my lectures long enough, you know that 3 is one of my favorite numbers. I don't know why I always gravitate to it, but it is what it is. So y equals 3x squared. First of all, I just want to graph on this, since this is a nice pretty looking graph. I'm going to graph on this, again, the regular parabola that we just graphed, the y equals x squared. Maybe I'll do it quickly. So I just want to make sure that people know that that's y equals just a regular old x squared. What I want to do here is graph y equals 3x squared. So let's make a table of values. X and a y value. And again, I'll try to make it symmetric about x equals 0. So we'll plug in a negative 2, a negative 1, a 0, a 1, and a 2. When x is negative 2, we get negative 2 squared, which is 4, times 3, which is 12. When you plug in negative 1, you get negative 1 squared, which is 1, times 3, which is 3. Plug in 0, you get 0, and so on and so forth. So let's go ahead and plot these points. I'll plot these in this obnoxious looking purple color. It's a different size pen there. One thing these two tables have in common, or these two graphs will have in common, is that they both have the point 0, 0. But beyond there, there's a slight difference. Like, for example, in y equals 3x squared, when you plug in a negative 1, the output is a positive 3. And when you plug in a positive 1, the output is also a positive 3. When you plug in a negative 2, the output is actually off the charts here. It's way the heck up here. So you won't be able to see it on the screen, but I'll plotted up above. And same thing when you plug in positive 2, it's at 12, so it's way off the screen. And when I go to connect these dots, trying to be somewhat smooth with the curve, but it's very difficult when it's this steep. You see, if I can do this nicely, that they have the same basic shape, but that purple line, which is y equals 3x squared, that purple line right there, a lot of students say that it looks narrower, and it's true, it does look it. It's actually considered to be stretched. So this is kind of an interesting result, is that when I compare it to y equals x squared, the graph of y equals 3x squared has been stretched away from the x-axis. In other words, you can imagine me smearing these red values up by a factor of 3. So every red value on here got multiplied by 3. So this red value at a height of 1 got multiplied by 3, now it's at a height of 3. This red value here that was at a height of 4 got multiplied by 3 and is now at a height of 12. So on and so forth. Everything's 3 times higher. The same thing is actually true if I had originally asked to graph y equals 1/3 x squared. If I asked you to graph that, you would again just build a nice little table, x and y's, and I would still do the same values here. But in this case, when you plug in a -2, well, -2 gets squared, so it's 4 times 1/3, that's 4/3. When you plug in a -1, well, -1 squared is 1 times 1/3. It's a regular old 1/3. When you plug in 0, though, you still get that 0 back. And so on and so forth. And when I plot these points, and let's see, I've used red and purple, so let's use black. We'll just use regular old black for the this final curve, y equals 1/3 x squared. It goes through 0, 0, just like the other ones. When x is 1 or -1, it's at a height of 1/3. So that might be right about there. Right about there. And when x is 2 or -2, the height is 4/3, which might be about here. Here, remember 4/3 is 1 1/3. So if I were to connect those points up, you see that this curve is not as steep as y equals x squared, and in fact it's definitely not as steep as y equals 3x squared. So the black curve here is y equals 1/3 x squared. Now comparing each of those, you could easily see that, well, look, that 1/3 is wider. That's what a lot of students say, but I'm going to say that it's not wider. It's just a factor of 1/3 closer to the x-axis. So in other words, each of these points, like this point here is a height of 4. Well, that's for y equals 1x squared, but for y equals 1/3 x squared, that point will be 1/3 of that height. It was at a height of 4, so 1/3 of 4 will be 4/3, which is exactly where that point is. This brings forth the idea of what's called stretching and compressing in mathematics. So what we've just witnessed is that the graph of y equals some number times x squared looks just like the graph of y equals x squared. They both look like parabolas, except if the number that's multiplying the x squared is bigger than 1, so like 3 in the case we just looked at, then the graph has been stretched vertically by a factor of a, by a factor of 3. Everything's 3 times taller. Likewise, if the number that is in front of the x squared, the coefficient of x squared, is a number between 0 and 1, and the previous case we looked at, the coefficient was 1/3, then the graph has been compressed vertically. In other words, has gotten closer to the x-axis by a factor of a. So let's do an example here. This is a good kind of question to ask for any student. Should the graph of y equals 10x squared be a stretched or compressed version of y equals x squared? What this is telling me is that y equals x squared looks or basically y equals 10x squared, looks almost like y equals x squared, except everything's 10 times as tall as it used to be. Well, let's go ahead. First of all, you know by the last theorem that I just wrote down that this should be stretched. It should be stretched. So I'm going to highlight the word stretched there. And let's just show that that's true by plotting some points. So I'm first going to plot the points for y equals just regular old x squared. And I'll just plot them really quickly. When x is 3, y will be 9. When x is negative 3, y will be 9 as well. So this is the regular old y equals x squared parabola. That's the standard, the gold standard for parabolas. Drawing freehand here. Y equals x squared. But the one I want to compare it to is y equals 10x squared. And if you think about it, you could create a table very quickly. I'm only going to plug in 3 points because I know what this is going to look like. When I plug in a negative 1, I'll get negative 1 squared is 1 times 10 is 10. This will be 0. That'll be 10. Plot the points. It goes through 0, 0, 1, comma 10, and negative 1, comma 10. And when I connect these points, you'll see it's extremely steep. Oh, I crossed the line a little too early, but that's okay. It's an extremely steep parabola. Trying to be exact. There we go. That red curve is the curve that represents all the solutions to y equals 10x squared. And notice how stretched that is. All the y values are 10 times higher than the y values for the green curve. This next question is a very similar question. This is asking me to compare again y equals x squared to another equation, or the graph of another equation, which is y equals 0.12 x squared. And so what I'm doing right now is I'm just quickly drawing out y equals x squared. The gold standard, again, this is the one all parabolas are held up against. All parabolas are pretty much judged as children of this curve. Okay, so this is y equals x squared. Now, without even graphing it, I already know it's going to be compressed. All the y values are basically being multiplied by 0.12. So all the y values in green here are being multiplied by 0.12, or they're 12% of the height they used to be. You can make a table of values if you want to. I'm just going to plug in negative 0, or negative 1, 0, and 1. And you'll find out that when you do that, you get the following values for outputs. If you want to even see what 2 and negative 2 will yield, you could plug those in. You get 4 times that, so it's 0.48 in both cases. And so I will graph this in red. They both go through 0, 0. When x is 1, it's just, oops, I had to fix that. It's just barely above the x-axis there. When x is 2, it's about at a half. I'm just going to mark that in there. And when x is negative 2, it's also at about a half. And you can even plug in a point like 3 and negative 3 if you wanted to. If you do that, you'll find that it's barely over 1. So I'm just going to go ahead and connect these points here. You get something like this. It eventually starts rising, but it takes a while to do it. So I can see all these values that were in green before are 12% of their height. Everything gets shrunk down to or compressed down to the x-axis. I'd like to illustrate this actually using a graphing calculator, just so that you could see the uses of a graphing calculator. Clear out this and I'll go up. I'm going to graph the regular old y equals x squared here. I'll zoom standard, so I'm selecting option 6. And that's the regular old parabola. And remember that when you're dealing with graphing, it's all accessed via that top menu on the TI graphing calculators. I'm going to hit y equals here, and I'm going to hop down to the next line to graph another equation at the same time. I'll graph 3x squared, and I'll graph, let's say, a 0.02x squared. So I'm going to graph three things at once here. First thing you'll see is the regular parabola, x squared. Next thing you'll see is 3 times that, which should be stretched version of y equals x squared. And the last one you'll see is y equals 0.02 x squared, which should be a parabola that's been compressed down to the x-axis pretty harshly. So here we go. There's the original parabola. There's 3x squared. And here comes 0.02x squared. It actually is a parabola, but it's so compressed down that it takes forever to rise up. So that's a good example. By the way, just to throw a wrench in the works, I could ask you what pi x squared looks like. Is it stretched or is it compressed? Is it a stretched version of y equals x squared, or is it a compressed version of y equals x squared? The reason why I ask this question is students often can't let go of the fact that pi is, they think that it's a symbol, or well, it is a symbol, but they think that it's a variable. It's not. It's a constant. It's just a number, 3.14 and some other junk on the end of it. So this should be a stretched version of y equals x squared because it's 3.14 blah blah blah. When I hit graph, you'll see, and it did kind of highlight in there. It took a while to do it, but it is there. Now, before I go any further, I need to talk about a few pieces of a parabola. The vertex. The vertex of a parabola, I'll just draw a parabola. The vertex of the parabola is the lowest or the highest point. So this is the vertex. It's essentially the bowing point. And by the way, not all parabolas open up. Some parabolas will open down. Okay, so that's a vertex as well. I'm freehanding this, so it's not the most beautiful picture, but whatever. By the way, that really poorly drawn parabola. Since I actually drew that poorly, I should probably say something else here. The definition for the axis of symmetry. There is this thing called the axis of symmetry, and if you look at a parabola, and this is going to be hugely important, oops, not symmetric, I have to write symmetry, write and not talk. If you look at a parabola, you'll notice that it's a mirror image of itself across a certain line. You just draw a parabola in free space here without any kind of axis on it. And there'll be a little line of symmetry, and this line of symmetry is this one right here. It cuts it in two, where it's a mirror image on both sides, and this line of symmetry is known as the axis of symmetry. We'll find out that it doesn't need to lie on an axis itself. So it doesn't have to be on the y-axis like our last examples. It could occur off of an axis. But that mirror image vertical line is called the axis of symmetry. And of course, it almost goes without saying that you have things like that is the y-intercept. It turns out that you can have parabolas that don't have x-intercepts, like this one doesn't. See, here's the x-axis, here's the y-axis. So not all parabolas will hit the x-axis, but sometimes they will, and they could hit it twice. So these are the x-intercepts. But like I said, it just depends on how the parabola is, where it's located, if it has x-intercepts or not. But what's interesting about parabolas, this is super important to understand, what's interesting about parabolas is that they always widen out. And so they'll always hit the y-axis. And that's always true because they're just an ever-widening U-shape. They keep widening out and out and out and out and out. No matter how far you want it to go to the right, it will keep going that to the right hand, or to the left-hand side or right-hand side. Now, I did show you an example of a parabola here that was upside down, let's take a look at how that could happen. And it'll happen, it's pretty obvious when you see it. Let's go ahead and graph, well, let's do a standard one. Y equals a negative x squared. What this is telling me is that this is going to look like y equals x squared, but all the y values will have a negative on them. So in other words, when I build my table, I can choose symmetric points, -2, -1, 0, 1, and 2. And when I plug in a -2, it'll get squared, it becomes 4, but there's a negative on it, so it becomes a -4. When I plug in a -1, it gets squared, it becomes a +1, and then you attach a negative to it, so it becomes a -1 again. Plug in a 0, well, -0 is just 0. Plug in 1, square it, and put a negative, it'll be a -1. Plug in 2, square it, becomes 4, throw a negative on it, becomes a -4. Let me go ahead, oops, do that. Let me go ahead and paste in here an axis, and we'll plot this. So here's 0, 0, -1, -1, 1, comma, -1, -2, comma, -4, and 2, comma, -4. And when I connect these points up, you'll see, oh, that's just our regular old parabola. It's just been flipped, or in other words, reflected about the x-axis. That gives us a nice theorem, so I'll go ahead and write it. The graph of y equals a negative x squared looks just like y equals x squared, the original parabola, except we flipped it or reflected it about the x-axis. That's a vertical reflection, so, as you can see in the last example right here. The standard parabola would normally look like this red curve that I'm drawing in here. It looks kind of like this, but the negative in front of y equals negative x squared there flips it. Now you can combine a lot of things that we've talked about. You can actually graph something like y equals -1/4 x squared. When you do this, I highly recommend that you read this from left to right and you show a picture for every single step. In other words, I would, notice I'm not pasting in any type of graph here. I'm actually just drawing freehand. I would draw the standard parabola first. The standard parabola looks kind of like this. You might want to, or you probably should, label points. That's the origin. I'm not going to label that. I'll call this 1, 1, and this is -1, 1. Remember, that's y equals x squared is the standard parabola. And then reading this equation from left to right, we'll start with the negative. The negative is going to take that picture that we just drew and it's going to flip it. It still has the same axis of symmetry. It still has actually the same intercept, the origin there. Just the only difference is that these points that were at x equals 1, 1 is now, this point is at x equals 1, -1. This point over here that was at x equals a -1, +1 is actually at -1, -1. And then finally, reading left to right, I will go ahead and take a look at, and maybe I'll just erase this so you can see it, take a look at the 1/4. So in other words, this is just the graph of y equals a negative x squared. I now want to attach to that the 1/4. So I'll go ahead and do that to see what this final graph looks like. Here's my x-axis, here's my y-axis. 1/4 means that it's everything's much closer to the x-axis. It's 1/4 of its original size. So it might be really wide like this. I mean, it's a curve, so I shouldn't draw it as a straight line. It's just hard for me to draw with this board. It still goes through 0, 0. This point right here, which was -1, not -1, that point right there was at +1, -1, is now at +1, -1/4. Because instead of being at a height of -1, you're at 1/4 that height. This point over here that was at x equals -1, y equals -1, is now at x equals -1, y equals -1/4. Notice the difference in the graphs. This is just a wider version of that last graph. And by the way, that is the final graph. That's the graph we wanted. Y equals a -1/4 x squared. And then yes, I do call these the simple graphs because these are the ones that you kind of hope to get. They all kind of share something very unique. Their anchor point, or in other words, their vertex. Remember, the vertex is the lowest or the highest point. So this is the vertex. This is the vertex. This is the vertex. The vertex is on the y-axis. That's what makes these very easy to deal with. When the vertex is not on the y-axis, you're in for a load of trouble. So let's change it up slightly and look at the graph of y equals x squared plus 2. Notice the difference here. Everything else that we've done has been attached to the x squared. We've had 3x squared, 1/3 x squared, -x squared, that type of business. But we haven't had a plus 2 or a plus 1 or a minus 1. So let's go ahead and make a table of values. Again, I'm going to be symmetric here. -2, -1, 0, 1, and 2. When I plug in these points, I'll get 4 plus 2, which is 6. I'll get 1 plus 2, which is 3. 0 plus 2, which is 2. 1 plus 2, which is 3. And 4 plus 2, which is 6. And I'll go ahead and plot these points. Bring this on over. Expand it out a little bit. Maybe I'll go ahead and graph the standard parabola first so that we can get an idea of what the standard parabola would have looked like. 0, 0, 1, 1, 2, 4, that type of business. I'll even go to 3, 9. Just so that we can kind of get a visualization of how this compares to the standard parabola. So the standard parabola would have been this red curve. And then the parabola that we want to graph, if I finish this up, parabola that we want to graph is going to go through not 0, 0, but actually this is the part that changes. It goes through 0, 2. So it's way up there. But notice it's been shifted 2 units up, which matches this 2 right here. And then when x equals 1 or -1, the height is 3. And when x equals 2 or a -2, the output is 6. And if I connect these points, I'll get the same graph, I promise. It's just been lifted up 2 units. So the purple graph is y equals x squared plus 2. And that gives us our last theorem for this lecture. The graph of y equals x squared plus k, where k is just some number, like in our last example too, looks just like the graph of the standard parabola, except it's been shifted vertically k units. If the number is positive, it's been shifted up that many units. If it's negative, it's been shifted down that many units. And that should make sense. Essentially, this is saying that all your y values are just like x squared, y equals x squared, except that you get to add 2 to each of them, or subtract 10 from each of them, whatever that is. So let's do a simple combined example, something that I can just make up. So let's take the example y equals, we're going to graph this by the way, a -3 x squared minus 4. So whenever I graph something like this, I take it in steps. I have the original parabola that I always graph. You label your axes, you be kind of thorough with this. And when you graph these, if you're not using graph paper, which is not that big of a deal, you don't really need to use it, what's important is that you know the shape of a parabola and that you can label points. I know that with a regular parabola, when I plug in 1, I get out 1. When I plug in a -1, I get out 1. That's y equals x squared. And of course, my vertex is at 0, 0. Now I read this from left to right. So I'll take care of the negative first. When I apply the negative, all it's going to do is flip this vertically, or in other words, reflect it about the x-axis. So again, I'll just label my x-axis, y-axis, and draw the same graph. It's just been upside down. Vertex is still actually at 0, 0. These 2 points, which were at a height of 1 before, are now at a height of negative 1. So that's a graph of y equals a negative x squared. The next thing, reading again from left to right, I'm going to attach the 3, which means everything gets 3 times as tall. So here's my x-axis, here's my y-axis. And everything gets stretched by a factor of 3. So this thing that was a height of negative 1 here is going to be at a height of negative 3 actually. This point that was a height of negative 1 will be a height of negative 3 as well. So you can see that it's probably going to fall very quickly now. In fact, maybe I don't want the point there. I'll label the point right here and here. And this point will be negative 1 comma negative 3. And this point will be 1 comma negative 3. But notice that our vertex is still at 0, 0. Because remember, all the y values are getting multiplied by 3 in this step. And 3 times 0 still remains to be 0. The last step here is to subtract 4. So I'm going to subtract 4, just again reading from left to right. This time I have to be careful of how I graph this, so I'm going to get my x-axis pretty far up here, because the fact is I know that I'm going to be moving this graph down. By that last theorem, the graph of y equals negative 3x squared minus 4 will look like this last graph here, but it's down 4 steps. So down 1, 2, 3, and 4 steps. So the vertex was at 0, 0. The vertex is now at x equals 0, y equals a negative 4. Otherwise, it's still that same narrow looking graph going down. But unfortunately, the points that I need to label will be off the screen. And that's essentially how you graph using the reflections and shifts up and down and stretches and compressions. And I'll have a future lecture on this for all kinds of graphs and things we call functions at that point. But for now, it's just an introduction to graphing quadratics.